Hello, my name is Elham Mohammadi, and I'm presenting this work on behalf of our team at National Bank of Canada, Concordia University, and University of Quebec in Montreal. So this work is titled Classification of Rare Recipes Requires Linguistic Features as a Special Ingredients. So first, I'm going to give you a brief introduction about this work. Then we're going to look into the dataset and the tasks which were addressed. Next, we're going to look into the methodology that was used to address the tasks. After that, we will take a look at the results and discuss them. And finally, we will have the conclusion. So what was the motivation for this work? It is true that in many real-life scenarios and applications, we have highly imbalanced data sets. So it's not the case that we have this clean and nicely balanced data all the time. And one thing that might be helpful in these cases is the extraction of discriminative features. Maybe these features can be used as well as distributed representations in a deep neural network, for example, to address a classification task where the dataset is highly imbalanced. So the goal of this work is the investigation of the effectiveness of using discriminative features in a task in which imbalanced data is available. So let's look at the datasets and the tasks. So the dataset used in this work was the DEFT 2013 data, which was, so DEFT 2013 was a shared task, and the dataset was made up of French cooking recipes, which were firstly labeled with their level of difficulty for task 1. So each French cooking recipe was labeled on a 4-point scale from very easy to difficult. And next, also for each cooking recipe, we have the meal type. So it can be either a starter, main dish, and dessert. So we have 2 tasks, one of which is a 4-class classification, and the next one is a 3-class classification. So let's take a look at the statistics of the dataset. So as you see, in task 1, around 50% of the data belongs to the very easy class. Next, we have 40% of the data going into the easy category, and less than 10% of the samples belong to the fairly difficult and difficult classes. In fact, less than 1% of the data goes into the difficult category. And this is true for all training, development, and test datasets. So this dataset is highly imbalanced. For task 2, which is the meal type of a starter, main dish, and dessert, again, we have 50% of the data, around 50% of the data belonging to the main dish class, and the rest split between starter and dessert. So again, we have this imbalanced data set, but it's not it's not as imbalanced as task 1. So the methodology that we used to address this task was using a joint model, actually for both tasks. So this joint model is made up of neural and linguistic submodels. So first, I'm going to go into the details of the neural submodel, and then we'll take a look at the linguistic submodel. So the neural submodel is, has different components. The first component is the embedding layer, which can either use pre-trained BERT or pre-trained Camembert embeddings to take as input a sample cooking recipe and output the dense representation. This embedding layer is followed by a hidden layer, which can be a choice of either a convolutional neural network or a graded recurrent unit. After the hidden layer, we have the pooling layer, which is attention in the case of the recurrent network, which is GRU, and either average or max pooling, or a combination of the two, based on which one is more effective. So that's the neural submodel. For the linguistic submodel, the main part is the feature extractor, which takes as input a sample cooking recipe and outputs the discriminative features associated with that recipe. And actually, the extraction and selection of these discriminative linguistic features was done according to the paper written by Charton et al. In 2014. It would be nice to take a look at that paper to gain more information regarding these discriminative features. So after this feature extractor in the linguistic submodel, we have a fully connected layer to transform these sparse representations into dense ones. Next, we have a fusion component which takes the outputs from both neural and linguistic submodels, concatenates them, passes them into a fully connected layer, and finally maps that to an output layer with a softmax activation function, which turns the output into class probabilities. So in order to check the effect of adding the linguistic submodel, we did several experiments. The first set of experiments were done using the joint model. Next, we did a set of experiments using the independent neural-based submodel in order to see how different the performance would be if the linguistic submodel was removed. And in order to check the effect of keeping the pre-trained BERT or Camembert embeddings frozen or fine-tuning them, we did a third set of experiments fine-tuning BERT and Camembert models. So let's take a look at the results. So in this table, you can see the results for task 1 on development and test datasets according to accuracy, macro averaged F1, macro precision, and macro recall. So first of all, here you can see that the joint model has superior performance compared to the neural counterpart. So almost like in all of the experiments, in terms of accuracy and macro F1, the joint models actually perform better. And we can also see a general pattern of improvement based on macro precision and macro recall when the linguistic submodel is added to the neural submodel. Also, we can see that features captured by the neural network can be complemented by the linguistic features. In general, models that utilize Camembert actually perform better. In fact, the joint CNN Camembert model outperforms the best baseline, which was achieved by Charton et al. In 2014 in the DEFT 2013 shared task. So in terms of accuracy and macro F1 and recall, the joint CNN Camembert model achieves the best performance and actually achieves a state-of-the-art results in this task. In order to gain a better understanding of how these models perform on each individual class, let's take a look at per class results. So here in this table, you can see the per class results for the very easy, fairly difficult, and difficult classes by different models. First, the neural ones, and next, the joint models, which have the linguistic component added to them. So here, in 3 out of 4 classes, the best F1 is achieved by joint models. And in fact, joint models that use Camembert. Actually, we can see improvement after adding linguistic features to the models that utilize Camembert, but this cannot be said about models that utilize BERT as their pre-trained embeddings. So we hypothesize that the linguistic features complement Camembert embeddings more effectively than they complement the BERT embeddings. And also, The joint CNN-Camembert model has the highest F1 score of 25% on the difficult class, which is a significant improvement compared to the neural model of CNN-Camembert, which is only 9.8%. And I would like to remind you that the difficult class is actually really rare, with less than 1% of the data samples belonging to it. So this 25% is very valuable here. Also, you can see that only 3 out of the 8 models achieved an F1 score higher than 0 on the difficult class, 2 of which are joint models that utilize linguistic features. And this shows the effectiveness of linguistic features when the task involves a really rare class in a highly imbalanced dataset. Let's move on to the results for task 2. So here you can see the results for task 2 by different models on development and test data in terms of accuracy, macro average, F1 precision, and recall. First of all, you can see that fine-tuned Camembert models have the best performance on the DEFT data, while the joint CNN Camembert model has the best performance on test data. So we can assume that the joint CNN Camembert model actually can generalize better to new samples. This model also has the highest macro F1 and recall. However, it falls short of achieving the highest micro score by 0.3% and the highest macro precision by 0.4%. So actually this model, although it is an improvement compared to the neural models, it still cannot achieve a state-of-the-art performance in task 2. Now let's go into the details of the per-class performance in task 2. Here you can see the F1 scores achieved by different neural and joint models on different classes of starter, main dish, and dessert. So you can see that the joint CNN Camembert model achieves the highest F1 score on all 3 classes on the test set. And actually, this model achieves a state-of-the-art results on the class starter, which is the rarest class in the dataset in this task. And this is actually in agreement with our hypothesis that the strength of this joint model lies in handling of rare classes. You can also see that all joint models here outperform their neural counterparts based on accuracy and macro scores. However, this improvement here is not quite enough to achieve the highest accuracy, unlike task 1, in which the joint CNN Camembert model actually achieved the highest performance based on accuracy. So in short, the joint model is more effective in addressing task 1 compared to task 2. And why is that? We assume that the linguistic features used for task 2 might not be quite as representative of the classes as the linguistic features extracted for task 1. And maybe another reason is that the linguistic features for task 2 are significantly more sparse. So, excuse me, so they are not quite as well adapted to this task as the linguistic features which were extracted for task 1. And another reason might be that we actually saw that the improvement caused by the joint model is higher in case of rare classes. And we also know that this imbalanced dataset, the case of the imbalanced dataset is more significant in case of task 1 compared to task 2. So maybe this is the reason why the joint model is performing better in task 1. Because as we already mentioned, the strength of this joint model is in handling of the rare classes. So the improvement there is simply more significant. So I would like to briefly point out a couple of points from this work. So in both tests, the joint models outperform their neural counterparts. And also, the improvements by the joint models is higher in task 1 compared to task 2. Also, the improvement by the joint models is more significant for the rare classes. So in case of starkly rare classes, this improvement is more significant. And finally, the strength of the joint architecture is in the handling of the rare classes. That brings us to the end of this presentation. Thank you very much for your attention.